Water and electricity behave in a very similar manner. Water can be described using pretty much only two parameters when we're talking about water in a pipe system. If we're talking about water in a pipe system, we'll describe the pressure of the water within the pipe, and we'll describe the flow rate of the water in that pipe. Electricity, similarly, can be described with two parameters. Instead of using water pressure, we say voltage potential. That's that electric pressure that's pushing these electrons. And similarly to water flow rate, how many water molecules are moving through the pipe, we need to know with electricity that electrical flow rate, how many electrons are going through. So let's take a look at this next slide where I relate these parameters. So if we were to take the concept of force, the thing that's generating motion, we're talking about a hydraulic system, we use the term pressure. The units for pressure might be PSI, might be bar, you might use water column. It's all the same thing describing a force that's distributed across the water. Electrically speaking, we use the term voltage. The units for volts are volts. Again, voltage is just like pressure in water systems. If we were to talk about flow, how much of something is moving, we use flow rate in water systems. That could be gallons per minute, liters per hour. And in electrical systems, we describe the current. The units for current are amperes, or more simply amps. Now, these next two slides are the most important slides to remember. Remember that when we're talking about electricity, when you hear the word volts, that's just the electrical word for pressure. Voltage is the force or the pressure that's acting on these electrons that generates the flow, that generates the current to be moving through the wire. It's generating these electrons to move. And when we talk about flow, current, electrical current, current is what happens due to the force, due to the pressure, the voltage. All right? So current is the resulting number or rate of electrons flowing through a cross-sectional area of the wire. In addition to those two parameters, we also need to bring up resistance. Hydraulically speaking, that's going to be your friction factor, your head loss on a pipe. How much resistance to flow is there? In electrical systems, we call that ohms. It's a strange word. We use the Greek symbol omega to represent that. But electrical resistance is what slows down the flow of electricity. Examples of electrical resistance could be a really long stretch of electrical wire. That's going to have resistance. That's going to make it more difficult to push those electrons through. Other examples could be a light bulb, might call it a resistor, a pump. All of those are examples of resistance. These three parameters, I think, are best described using this photo here. This describes its relationship. There's a law called Ohm's Law, which is simply the voltage is going to be equal to the multiplication of your current and your resistance. Now, we look at this photo. It's kind of a funny photo, but we have the volts, which are pushing the amps through the wire. But those amps don't get to just go freely and easily. The ohms are resisting, they're restricting the flow of amps, okay? And then if we remember this relationship up here, it's a very simple relationship. If I were to leave voltage the same, double my resistance, I'm only going to get half the amount of amps through my system. If I were to double my volts and leave the ohms the same, I'll get twice the number of amps through the system. So just remember, it takes 1 volt to push 1 amp through 1 ohm.